Infinity. Infinity is not an obvious concept, but extraordinary in a way. Infinity pertains also a set of numbers, or especially a set of numbers. For example, natural numbers like 1, 2, 3, 4, 5, 6, 7, and so on, which are very basic mathematical objects that are very often used. Nevertheless, infinity eludes what is known as universal and strict mathematical analysis. It's not surprising that we humans have a desire to tame infinity, to understand it. Professor Georg Cantor and his followers tried very hard to understand and describe infinity. But did they manage to achieve real success? Many in Professor Cantor's time highly doubted this, while many currently living strongly believe in this. I will no longer keep you in unjustified uncertainty. For sure a bit surprising for many of you, but the only correct answer to the question, did Professor Georg Cantor achieve a real success in understanding and describing infinity, is no. The theory of infinite sets, initiated by Professor Georg Cantor and developed by his followers, aspires to be a correct description of the infinite sets reality, relationships between infinite sets and their elements. However, the truth is, this is simply description fallacious. From the history of science, we know the cases, sometimes very spectacular, when the great theories, accepted by everyone, turned out to be completely flawed or at least very imperfect at some points. As a result, such theories were either completely rejected or thoroughly revised. The same is about to happen, there is no other way, with the set theory by Professor Georg Cantor. In this presentation and in the following ones scheduled for the coming weeks, numerous errors of set theory will be revealed, exposing step by step wide extent of its aberration. I invite you to watch, listen and observe how the stars of the world of science are falling. Adam Polak. Cantor's diagonal method faulty. Case 1. Quantitative equivalence of the infinite set of real numbers and the infinite set of natural numbers by analogy with the Hilbert paradox of the Grand Hotel. A detailed description of the Hilbert paradox of the Grand Hotel can be found, among other places, on Wikipedia and in many presentations available on YouTube. The essence of Hilbert's paradox of the Grand Hotel boils down to the following assumptions. Consider a hypothetical hotel with a countably infinite number of rooms, all of which are occupied. This description gives us the following assumptions. The hotel with an infinite number of rooms. There is a guest in every room. As a result, we have two infinite sets. The infinite set of rooms collecting elements with the following symbols. R1, R2, R3, R4, and so on. The infinite set of guests collecting elements with the following symbols. G1, G2, G3, G4, and so on. A new guest appears. Symbol of him is NG1. The new guest is definitely not among the guests that are already in the hotel because he is different from them. His name is NG plus its individual number 1. Before the new guest arrived, each of present in the hotel have the name G plus individual number of each of present guests, 1, 2, 3, and so on. If we accept the claim that we can accommodate a new guest in room number 1 and move everyone currently present in the hotel to rooms n+1, we cannot deny that exactly the same operation can be performed for new real number supposedly created by Cantor's diagonal method. Here we have the presentation of two infinite sets. At the left, the infinite set of rooms. At the right, the infinite set of guests. New guest appears. We intend to accommodate new guest NG1 in room number 1, R1, where currently stays guest G1. And we claim to move all guests currently present in the hotel to the room number N+1, comparing to the room where they currently stay. Finally, we have new guest NG1 in room number 1, previously present in the hotel guest 1 in room number 2, guest 2 in room number 3, guest 3 in room number 4, and so on. Regardless of what quantity of new guests will be accommodated in the hotel, the infinite set of rooms will represent always the same quantity of elements as the infinite set of guests, previously present and new ones. These two sets always represent the same quantity. They are quantitatively equal at the end of all operations, never mind how many such operations will be done. Precisely the same scenario takes place if we replace the infinite set of rooms with the infinite set of natural numbers and the infinite set of guests with the infinite set of real numbers. What you see on the screen now is Cantor's diagonal matrix. In left column we have natural numbers. In right column we have real numbers in random order. Now, as it always takes place, we pretend to create a new real number. In this case, we increase each following diagonal number by 1. So, in the first real number on the first position we have 1, we make it 2. In the second real number on second position we have 2, we make it 3, and so on. Precisely in the same way as that was in Hilbert's paradox of Grand Hotel, we intend to assign new real number to natural number 1. And we assign each real number that was previously assigned to natural number n to natural number n+1. Finally, we have new real number assigned to natural number 1, and each real number previously present in the right column is now assigned to natural number n+1 comparing to the natural number which they were previously linked with. The mechanism is very simple. This is one-to-one analogy with Hilbert's paradox of the Grand Hotel, and this is impossible to deny. Of course, an infinite quantity of new real numbers can be added to the infinite set of real numbers, and of course it will remain in quantitative equivalence with the infinite set of natural numbers. The statement that in Hilbert's infinite hotel a new guest can be accommodated, and even infinitely many new guests, is mutually contradictory with the statement that it is not possible to find a natural number as a pair for the new real number created by Cantor's diagonal method. If we claim that we can accommodate a new guest in Hilbert's infinite hotel, we cannot deny that exactly the same operation can be performed for a new real number, supposedly created by Cantor's diagonal method. In light of the presented analysis, Cantor's diagonal method cannot be indicated or treated as evidence in any way confirming a greater quantity of elements in an infinite set of real numbers compared to the quantity of elements in an infinite set of natural numbers. As mentioned at the beginning, the set theory, creator of which is considered to be Professor Georg Cantor, currently headed by the vast majority of scientists, is flawed theory, based on mistake assumptions and, as a result, filled with errors and internal contradictions. The presented arguments are sufficient to assert that Cantor's diagonal method cannot be indicated as a tool that in any way proves a greater cardinality quantity of elements in an infinite set of real numbers compared to cardinality the quantity of elements in an infinite set of natural numbers. It should be emphasized that this presentation is not an illustration of the only error contained in Cantor's diagonal method. Other errors will be identified and indicated in subsequent materials. Presented case was just the starting one, basic one, very easy to understand, I think, but very important. Of course there is no list of all real numbers, precisely the same as of course there is no list of all natural numbers. I can prove it to you, show it to you in the way that no one will be able to deny. So, if you have any questions, do not hesitate to ask in the comments or sending me an email. Of course, I invite you to follow next presentations. I have very limited time, but I will try to put them online as quickly as possible. But you can speed up on your own. You have available this. So, the description and the analysis of a significant part of set theory errors can be already found in one of previous presentations on channel AP211. It's titled Georg Cantor's Set Theory Collapse, One and the Only Infinity, N equals R Final Proofs. I welcome you to read. If any questions, I will try to answer. Thank you for watching, and I hope so see you soon during this very interesting and important adventure. Adam Polak.